Good evening. Welcome to every one of you. And I also take this opportunity to welcome Dr. Lakshmi Narayanan for this evening event. Thank you, sir, for accepting our invitation and making your presence in this event. Just to introduce, he is, of course, a very well-known person. For younger audience, I would like to sort of give a little introduction to him. He's a distinguished leader in the global IT industry, best known for his pivotal role as a co-founder and CEO and vice chairman of Cognizant. With over 4 decades of experience, he was instrumental in transforming the company from a small startup into a multinational powerhouse. Of course, he is also a product of IISc Bangalore and had an overlap with Professor Bhaskaran, so he had some connection with us. Before his time at Cognizant, he spent 19 years at Tata Consultancy, TCS, where he rose to a leadership position, gaining the foundational experience that would later define his career. He also served as a chairman of NASSCOM, an influential industry body. Beyond his corporate achievements, he is also a dedicated figure in education, philanthropy. He currently serves as a chancellor of Priya University, our neighbor, and is the managing trustee of Chennai Mathematical Institute, which is in some sense, it's sister institute actually. Okay, so he has other connections with our institute. As a prominent angel investor, he actively mentors and supports a new generation of entrepreneurs, focusing on deep tech, enterprise applications. He also channels his philanthropic efforts through non-profits like United Way, where he works to create livelihood opportunities and support disadvantaged communities, actually. Thank you, sir, for coming. I think most people will join, actually, for this panel discussion. So I'll hand over this to Steve, who will actually run the remaining part of the program, actually. Thank you. And before he takes over, I would like to, Dr. Lakshmi Narayanan to say a few words about
No, this is fine. This is fine. Actually, if I raise my voice, I think most of you can hear me even without the mic. Thank you very much for this introduction, and it's nice to be here. Congratulations on this celebration that you have. Fantastic to be in this auditorium and to this great institution. We often talk about IMSC from CMI and also in Kriya, and I must thank all the people who are supporting both Kriya and CMI. I know many of you have come and lecture. He was there. Govindarajan is there. He continues to help us. And before coming here, we were just talking about what are the things that are happening generally. So maybe I'll stick to that, because as much as you understand, as much as he has said about all the good things that I have done, you will realize my ignorance at the end of my talk. So I'll stick to what I know, what I've been doing, which may be of interest to you. Quantum is something that many people are beginning to, it may be interesting to talk about an interesting anecdote. Most recently, this is something that happened about a week back. There's a person known as Damodaran, Ashwath Damodaran, a very famous person. He teaches corporate finance in Stern University, known as the Dean of Valuation globally, recognized as a person. So he was asked about artificial intelligence. So what do you think about artificial intelligence? Will it be a great success, as many people make it out to be? Or will it not deliver the promises that it holds? a similar question can be asked about quantum and quantum computing also. So his answer was, he referred to Blaise Pascal, one of the philosophers, physicist, theologian of the 17th century. So during those days, the debate apparently was about the existence of God. God, does he exist? If he remain good, will he take us to heaven, or do we have to suffer in hell? That was the question. So there is a Pascal wager that it is called. He just said, typical 2 by 2, you can be a believer or not a believer. But if you're a believer, it turns out that God is really there. You have got the jackpot, you'll go to heaven. If he's not there, doesn't matter, you haven't lost. But if you are not a believer and God is real, you have lost. So whether AI would deliver or not, you better believe it. So if it turns out successful, you're okay. And I think quantum is probably in a similar state as far as many other things are concerned. But in the last 3 months, I met 2 people. My interest is primarily in quantum computing, the applications, and more importantly, quantum algorithms. Are there people interested in that, developing algorithms? What is the state of the art as far as that is concerned? So I do come across people. The most recent one is a person from Madurai. You must have heard of Gopal Krishnan Balasubramaniam. Gopi Balasubramaniam. Yeah, he's at the quantum. He was here recently. Had opportunity to spend some time with him. He talked about his company, ExceedQ. It's a company that he has started. He has 4 quantum computers, 4 qubit quantum computers that work at ambient temperature. He has manufactured, delivered it for research purposes to about 4 companies in Germany. He's based in Germany. He worked in Max Planck Institute, etc., etc. So Siemens, some of the big companies in Germany are using that computer for experimentation purposes, trying to develop algorithms, etc. And he's very excited about his company as well as that quantum computing that he is doing. And I just asked him about what are the comparable things that are going on in the industry. And of course, IBM has its own Quantum One that they're using. Google has its own IonQ, which they say that they're using it in the cloud marketplace, so on and so forth. So there is a fair amount of activity that's happening, but nothing earth-shaking yet as far as its application is concerned. Okay, there are applications they talk about in the area of healthcare, molecular biology, in the nuclear reactors. That's another one interesting topic. Maybe I'll touch upon that before I close. So that is the state of the art as far as computing is concerned. But I believe that there is a lot more of theoretical work that needs to happen in order for these companies to be successful and more algorithms to be developed. There isn't they're saying a Java virtual machine running on a quantum computer is kind of the holy grail. Not there. Then once that kind of a thing is achieved, then we can say more and more applications can be developed using quantum computing. Some of the real world problems can be solved. In the area of nuclear energy, Anil Kakotkar is associated with this. Anil Kakotkar is associated with Chennai Mathematical Institute. I'm also associated with Anil Kakotkar in a company called Clean Core Thorium Energy. I don't know how many of you have heard of that company. This is a US-based company that has developed thorium-based nuclear fuel. Thorium combined with what they call the high assay uranium and formulated a thorium-based nuclear fuel that will change the nuclear fuel cycle progressively over a period of time. And this is something that has been, the research was carried out in the US with the help of a number of people from MIT, guidance provided by Dr. Anil Kakotkar. In fact, the company CCTE named that fuel Anil, A-N-E-E-L. It's called Advanced Nuclear Energy for Enriched Life. They didn't want to call it Anil. Anil said, I don't want my name associated with that, although I may have done some significant amount of work. I don't want it because politically, if my name is there, it won't go anywhere in this country. So that fuel is formulated. It has gone through 2-3 rounds of testing in the Idaho Nuclear Laboratory. That's the world famous nuclear fuel testing complex. The thermal output, the burnout is reached something like 45 gigawatts and expected to go to something like 60 gigawatts, which is almost 3.5 to 4 times the type of nuclear fuel that we are using currently. And it is proliferation resistant. The wastage is much less than the current uranium based cycles are used. And the most important thing is this thorium based fuel, the pellets of which are being made in the US, because we are not allowed to make it here. They can go into our PHWRs directly and be used immediately. So there is a demonstration irradiation project that finally the DAE, NFC, NPCI, they have agreed to do the demonstration irradiation of this thorium fuel. And for that, we have to get the permission from the US government. Under the Civil Cooperation Agreement, the Department of Energy has to permit that company in the US to export to India. It's called the CFR 810 Energy Certificate. 2 weeks back, the Department of Energy granted that certificate. So we are ready as soon as any of the nuclear, the DAE, the departments are ready. It can be tested. So the actual full use of it will probably take some time because it has to be tested, demonstrated, etc. in the Indian context. The reason I mentioned that is because if you're talking about SMRs, and if it is going to be privatized and private companies which have expressed interest in building these nuclear reactors, okay, there is a fuel that is available which is very different from the fuel that we have. And more importantly, we have rich reserves of thorium. And we don't have to be dependent on external entities for power generation in this country, which is one of the key ingredients for all the computing that we want to do. So while there is a lot of activity that is going on, both at the scale at which people like Dr. Anil Kakotkar and the DAE and all the government entities operate, there's also at the entry level, there's a lot of work that's happening. One of the things that we talked about was the brain research and the data that is available. How can we use that in order to gain insights? There's another company that I was talking about that I met in Indian Institute of Science, a company called Zero, ZIROH. They claim that they can deliver the computing capability of a GPU in CPUs through the special software and the special software that they have. It sounds interesting. They talk a good game, but we'll have to see how practical it is. So one of the things that I notice in all these things is the collaboration between academic institutions and the industry, particularly the startup industry, is very, very light. It is, I'm sure several people have tried to find a model where some of these things can work, where there is an intense cooperation and collaboration that happens between this. The best known experiment so far remains to be the IIT Madras Research Park. And of course, other institutions have also tried. The instance where one of the professors mentioned in IISc where there is a vaccine development that's happening. Bulk of vaccine development nowadays apparently happens on the computers, and they get to a stage where a molecule is formulated and then they go for field trials. He says there is a collaborative work that has to happen. Industry, they go to IISc, that company, they go to a Biocon. Biocon says, that's not my specialization. My area of specialization is enzyme. Vaccinology, you have to go to either Serum Institute or Bharat Biotech or one of those companies. So if you approach them, they will say, we have a certain level of expertise, but then in terms of collaborating the fundamental science, we'll have to either go to IISc or go to NCBS or go to some cellular institute, etc. But all of them coming together on a common platform is something that we have not been able to achieve it. I think that will provide clearly a multiplier effect if everybody collaborates that. And some of that collaboration will happen among the younger students. Students are far more adept at reaching out, being aggressive in terms of calling people and getting into meetings, etc. The students need to get that type of an exposure by visits, etc. Again, I must congratulate Govindarajan for the work that he is doing with Kriya University students, taking them to a Kalpakam site and showing them what's happening there. Those are all such inspirational stories. Even if 2%, 5% of the students get inspired and get into this line, want to pursue the research and collaborate with others, we would make a huge difference. So these are the points that I wanted to make. And I must congratulate once again the organizers for organizing this. I believe there have been fantastic lectures that people have been listening to. Somebody mentioned that, I think Bhaskar mentioned, Shankar gave a terrific talk. I wish more students would come and join here. This is remains a well-kept secret. If it has been publicized to all the educational institutions, I'm sure so many of the faculty may have come and attended this conference. Perhaps that's something that we can do the next time this happens. Thank you very much, and all the best for the rest of the deliberations here.
Okay, thank you, sir, for inspirational speech, and let's move on to this panel discussion. I think I request Trustee Hari to take over. Yeah, please. Please.
Thank you for your insightful remarks. You told about Gopi Balasubramaniam's quantum computing. It's a remarkable effort. 4 or 5 qubits, it's a quantum computer which is operation at room temperature. Following his lead as well as independently, IIT Madras has been growing artificial diamonds and NV centers, and there's a whole group of 6-7 people, my colleagues, working on it very seriously. And in fact, I'm trying to connect Gopi with them, because it turns out Gopi is the son of my MSc classmate, Balasubramaniam. So I knew him from his younger days. So it's wonderful work. So that is one remark I wanted to make. So NV Center definitely has a great promise, and it's slowly coming up. The second one is about your fusion reactor. Recently I keep hearing about electrochemistry enhanced fusion phenomena. It's not cold fusion that, apparently there has been significant increase in fusion when there is an electrochemistry. So somebody sent me a couple of papers, I'm looking at it. Then I remembered my professor at Bangalore. He had some estimates of how whenever there is a defect in a solid is moving, it can be sound velocity, so that can overcome Coulomb barrier and that can cause occasional fission. So I'm going back to it, and so nature is wonderful and many, many things are happening. So I just wanted to make these 2 remarks. Thank you very much for wonderful.
Thank you. Sri, can you?
Okay, so we can move on to the panel discussion now. So I would like to call upon the speakers of today to come on stage, and we'll follow the same format as yesterday. If people have questions, we can raise those questions, and any discussions that we would like to have is welcome. Okay, so let's get started. Are there any remarks that any of you would like to make before we start, or shall we open it up to question and discussion? Anything that you would like to say which you didn't have a chance to talk about in your talk? Is it?
Yeah, just wanted to comment about the involvement of academicians with the startups. So at ICER Pune, we have a Section 8 company on quantum technologies, and we are starting to develop an ecosystem where startups who have their own institute as well as other institutes, we are slowly trying to get them involved and together with us so that they get some support from the academicians and the facilities that we have. Because especially in the area of quantum technologies, even buying a high-end oscilloscope which costs several tens of lakhs is not possible to be bought by the startups. Instead, they should concentrate on their focus on their core area, and then if they need any support, we are there to give. So, in fact, a couple of startups came out of our students also. Yeah, and we keep supporting these people in whichever way we can, in all legal ways. Yeah.
That also reminded me one thing. Last year we started Masters in Quantum Technology. So this is a new Masters program in ICER Pune. Yes. So this year we are in the second batch now. We have taken second batch. So they will do 3 semesters of courses in ICER Pune. And during that time also they can do summer project elsewhere, and they can do online projects also elsewhere, but physically they will be there for 3 semesters. And 4th semester we are encouraging them to go to industry so that they can get industry experience. So that's the pattern, and so the goal is to connect with the industry and feed manpower to the industry. So, and since you mentioned students, so that's the initiative that we have.
And this industries also include startups. So they will also see that side of the story as to how to.
So I was just curious, are, like companies like Cognizant, are they taking up quantum, computation and things like that in a big way, or just waiting and watching for now, or what?
Just waiting and watching at this.
Yes.
Believers, but not doing anything.
Okay.
Just believe that it is going to be a big thing so that they don't get left out, but not even dipping their toe into it.
Yes.
Which company in India has gone into
I'm not familiar with any big company in India. If anyone does it, I think TCS R&D will probably be the first one to start this thing. But the big companies, the Googles of the world, IBM, they're experimenting with it. That's where it is. I don't, to the extent that I know, I don't think they have started doing anything there. Because normally our industry talks first before doing anything. So since the talk hasn't happened, that means nothing is happening in that area.
Okay, any other comments? Any comments from people before we open it up for questions? Yeah.
I'm curious about who will be the clients of these startup companies.
Okay, I mean, I should first tell you the products they are working on, the kind of products and the application area that some of them are working on. For instance, imagine, these are simple examples, okay. I mean, like one of the things is magnetocardiography, magnetoencephalography, quantum inertial sensors. So, yeah, no, so in terms of the direct applications, these are some areas. Like for example, you can imagine the entire healthcare system would benefit from those MEG and MCG systems. And say Q quantum, whatever, inertial sensors, the entire transportation industry, including strategic sector, would be interested in that, because these quantum sensors are supposed to be or have potential to surpass all the classical sensors that are used currently. And some of them at a much lower cost than what current systems allow you to do. Like for example, MEG, you don't have to sit in a zero Gauss room and use superconducting squid detectors to map the magnetic field on the head of the brain. You can do it at room temperature and at NV centers, atomic vapor cells, and yeah, these are all room temperature systems which can do it. Yeah. So those kind of, and apart from that, there are a lot of technologies which are enablers for quantum technologies, which are classical technologies. They are not, I mean, there is nothing quantum about that. For example, if you, for people who are building quantum computers based on various platforms, there are certain things which are common to all of them, like the control systems, the hardware which is agnostic to the platform that is going into it, and things like that. So those are classical technologies, but enablers for quantum technologies. That's a huge area, and also has multiple applications, not only in quantum technologies. It's just about capacity building, indigenous capacity building in developing high-end hardware.
Sir, this, I'm seeing them as still research problems, where I'm seeing all the startups are, clients are universities, and again it is going back to the academia rather than coming to the real world at immediate time.
It is possible because, of course, I mean, startups are entrepreneurs.
So
they take, no, let me tell it from my point of view. If I am a startup and I am a young person, I want to make significant impact in a particular area. To do that, I have to think completely out of the box. And many times, what I am thinking might not be the right path to achieve the goal, because you are experimenting and you are actually taking a leap. It's bound to fail. Out of the 10, even if 9 fail, if 1 succeeds, even if you, out of 100, even if 2 succeed, that's a good achievement from a national standpoint.
We need a lot of philanthropy.
Huh?
I mean, we need a lot of philanthropists to support these startups. It's just like an
No,
academia.
one of the things that has been missing so far is the willingness of investors to put in funding into these deep tech areas where you need what is called as patient funding. You put money and forget about it for 5 years, 10 years. That very few, that kind of appetite very few people have. Now, one of the things that the National Quantum Mission has done in the recent times, the government, is that they're saying that, okay, we will put so much money into the startups. That will give confidence to private investors to put their parts, so that these startups can get whatever investment they would need to actually succeed in the project that they are working on. Philanthropy, I don't know. You might be a better person.
Just 2 points that I want to make. One is there is a company called IntelliQuant. I don't know if you've, anybody has come across that. This is started by Dr. Krishna Palem. Krishna Palem is a researcher, well-known researcher, IBM researcher, fairly well recognized. His claim to fame is approximate computing. So the area that he's been working on is saying that not all the problems that we have needs complete total 20 decibel places, floating point type of a solution, approximate computing. So he's got a solution, an algorithm built in his company called IntelliQuant, a combination of quantum and classic computing. He's got a solution and he's going around looking for a problem. He's saying if there is a 50,000 parameter problem that you want me to solve, I've got the solution. But who's got that? So when we met him recently, a group of us connected him to two companies. One is Indigo, the airlines, for their scheduling. As they become 3 times their current size, what kind of challenges are they bound to have? How will that be solved? And the second company that we connected them to was the TVS Logistics, the company that has, tremendous. It's gone so global that they have very complex problem in terms of supply chain management and the logistics problem. So hopefully these are two applications where they might apply the solution that they have. And hopefully in the next 1 year, we will have some solution come out. That will be a kind of a trend setter for that. As far as funding is concerned, yes, that's always been a challenge. And every major institution is starting their own fund. IIT Madras is planning to start their own fund to support deep tech companies. IISc Bangalore is starting a fund to support deep tech companies. You mentioned that you have the funding. And generally companies like SIDBI, which is the Government of India organization, are willing to support, provided there is an academic support for whatever work that is happening. Okay. And the two institutions, BIRAC and IDEX, I don't know if you have heard of it, they've given a lot of funding to companies. BIRAC in the area of biological sciences, thanks to Professor Vijay Raghavan. And IDEX is the defense-related things, particularly in the areas of communications and signal processing. They've got a lot of work that is done.
And IDEX, one of the recent examples is that one of the startups got a funding of up to 25 crores for a quantum inertial sensing system.
I have another example. There is a company called QNU Lab. So QNU, right? QNU. And its market share, market capital is, I think, more than 1,000 crores, last I heard. Valuation. So their major client is defense. Okay, they are already networking defense connectivity by quantum key distribution. So you were asking clients, right? So I mean, just an example. So they are doing this, secure communication channels for defense. So there are many things. Sensing, quantum computing is not the only technology, because we, hear more things about quantum computer. Quantum computer may not come over next 5 years or even 10 years. We don't know. As he rightly mentioned, we need some earth-shaking breakthrough, right, to make it error-free. Right now, the focus is on getting the logical qubits where we can trust the quantum computing. Because every time if you want to cross-verify the results of quantum computing with classical computers, then it is not going to be useful. So you have to trust the results of the quantum computing. For that, they have to be by construction error-free, and that is done by theoretically by logical qubits and error correction and so on. That is still some way, some way further. But there are many other technologies which are quantum-based, quantum sensing, quantum communication, and quantum simulators and quantum optimization, as you mentioned. So all these things are much more realistic at the present. So there are clients for those products.
Yeah. Should I? So talking about this quantum computers, the gate-based quantum computers, of course, as is mentioned, I don't know, maybe 10 years or more when we would realize that, because that inherently, it's called digital quantum computer. Inherently, it requires that you don't have errors, like in classical computer when you manipulate the bits. But there is another thing within quantum computing, it's called analog quantum computing. Basically, you use, what you do is that you map a real-world problem onto something that physicists would like to call a Hamiltonian for a system, and map it onto one of the platforms, I don't know, neutral atoms, ions, or superconducting qubits, whatever, and then let the system evolve itself to a ground state. To some extent, D-Wave computers do that, but D-Wave, but they cannot do everything, because their systems are not very poorly connected and, well, whatever, it does its job in certain areas, but those problems for a very tailored system can work as analog quantum computers. Of course, recently there was news from Microsoft also that they have done, no, optical computing, purely classical optical computing. No, it's not even single photons. Not even single photons, I think. No single photons anywhere.
So can you say, what is the challenge right now on where we are right now, and to realize an actual useful quantum computer? What we can start with the word, and what do we need to achieve in order for it to be a realistic quantum? What is holding us back right now, which if solved we can move forward in a big way?
It's a very
Is it
it's a very tricky question, but
Okay.
I can tell you where we are.
all right?
So there are like 3-4 platforms which are at the top. Of course, superconducting qubits we have been hearing for a long time because that has been making a lot of noise and buzz. That status we know, they have 100 qubits or few hundred qubits, but nobody tells us about what are the error rates and how many gate operations they can operate and things like that, and what kind of realistic problems they have
The
solved.
coherence time and also the connectivity are
A lot of things. So everything boils down to something called as a quantum volume,
okay.
which IBM only came up with that term, which basically tells you about how many qubits you have, what are the single qubit times, what is the coherence time, what is the ratio of number, how many gate operations you can execute within the coherence time, then
How
how
about
many
the-
qubits are connected to
correct.
what. So basically, and what is the depth of the circuit that you can execute. So number of gates as a time sequence over all the qubits. Anyway, nevertheless, so that is one. The second one is the neutral atom computing platform, where they have created an array of up to 1,000 neutral atoms in vacuum. And one of the problems that they have, of course, also demonstrated 256 qubit logical quantum computer with that. These systems can also be used for analog quantum computing. Like one of the things that they did was they solved a similar logistics problem for the Manhattan Island. So you basically choose these qubits and connect them through Rydberg interactions and let that system find its ground state or whatever to solve. It's a toy problem in a sense, but these demonstrations have been done. Now, all these are small achievements which only kind of gives us hope to see some light at the end of the day, because there has been regularly incremental progress in addressing many challenges, scalability problems, coherence problems, then these problems related to other things like whether I can operate it at room temperature or whether I should take it to liquid helium temperatures, and also not only liquid helium temperature, even lower than that to dilution refrigeration temperatures, which again requires resources like helium-3, which is very scarce. So a lot of these challenges. But yeah, there is progress happening at a steady rate. So at the moment, I haven't heard anybody tell me, okay, to solve this particular problem, we need so many qubits and this error rates. You always hear some vague numbers like you need million qubits, thousands of qubits. I don't know. Do you know any of you heard about? Yeah. See, for example, the ion trap qubits, like we are working on, there are very few of them, but they have shown the best quantum volume.
So how do you connect to, is it a nearest neighbor connection in your case? If you have rubidium atoms in your trap.
Calcium atoms,
Calcium.
ions.
Okay, and then you want to connect them.
Yeah, you
How do you
can do nearest neighbor, you can do entanglement swapping from next neighbor, nearest neighbor to the next neighbor. You can do a global gate on all of them
You can do an arbitrary far connection? Is that?
through a global gate.
I see.
Also, you can unique three-dimensional lattice using the chain.
Yeah.
Perimeter has done recently.
Uh-huh.
Rasibul Islam,
Uh-huh. Yeah, yeah.
Waterloo Perimeter, he has done.
Mm.
So I just wanted to make a couple of comments, if that is okay. No, I think Lakshminarayan pointed out about the importance of theory experimental collaboration. Definitely it's a theory institute, we need to collaborate, which already is happening slowly. And another thing I wanted to mention about is this time frame that you said we have to wait for 5 years. I remember a beautiful article by Fluxner called Usefulness of Useless Knowledge. He was the founding director of Perimeter Institute for Advanced Studies, Princeton. He hired Einstein. He's asked the question, suppose somebody has to give award to posthumously for the communication revolution that we're enjoying. Everybody will say Marconi or J.C. Bose or Hertz. He says, no, it's Maxwell. Because what did Maxwell do? There were 5 distinct laws, Gauss's law, Ampere's law, Bayes' law, there's no connection. He put them together into the hands of calculus. He discovered electromagnetic wave equation. It predicted existence of electromagnetic at all frequencies. So light got connected to everything. So that was the power of theory and unification. So he had to wait 20 years for Hertz to discover it, 20 years later for communication. So he says open-ended science is very important. A small amount of money should be spent for open. In fact, I was telling Ajit Chaudhary when he was, when we were sharing, who is the head of quantum mission, that some amount of money should be meant for open-ended science. Don't worry about the result because it may affect the society in 50 years from now, not tomorrow. Because if you ask for a result tomorrow, they will produce a result today itself. There will be some. So I think that's something I wanted to mention. It's very important to have. Okay, the third point I will finish. Since I am spending more than half my time at Perimeter Institute, it's a remarkable institute of science philanthropy. Mike Lazaridis, the BlackBerry chief, he apparently wanted to become a quantum person when he was young. Poor guy who could only become a billionaire. So he had an opportunity, and he gave $100 million to do this open-ended science at Perimeter. Now he has given $400 million. He says, please don't write too many papers. Write papers that will help society maybe 100 years from now. I'm spending a small fraction of my money. I'm still a billionaire. He's also started something called Quantum Valley Investment in that area, where they're also investing. So I believe, since Lakshminarayan is here, involvement of private donors is very, very important because we cannot believe the government. Because government has their own priorities and their own compulsions. Whereas if you take Chennai alone, there are 10 or 15 billionaires. Even they give a small amount of money for open-ended basic science. Of course, other things, there are many, many important things. But I think open-ended basic science is important and we need to support it. Like in the present context, more exploration is to quantum. I was very delighted to see LODA supporting mathematical institutes through. So I wish there are more people from Chennai and other places. Bangalore, in fact, I gave a talk 4 years ago at NIAS. I said that you are sitting on a gold mine. Get existing philanthropists like Krish Gopalakrishnan and Lakshminarayan and others, and sensitize new people. They will come, but they have not started it. Anyway, thank you.
Okay, I will switch gears a bit, and I was thinking of one thing to ask Anant, if I may just start off.
Just before that, since Umakant here, he gave me the mic and said you should say something,
Please,
even though I'm not really qualified to say that. First of all, I'm very pleased to be from the institute which has 2 distinguished alumni sitting in the front row and 2 equally distinguished, somewhat younger alumni to my left. I have been listening to your observations, which are all valid. The only thing that I want to point out is, even though the Indian Institute of Science has an iconic presence in the country, we are hardly 350 faculty members. It's very small. I remember many years ago, the then president, Pratibha Patil, she came and said, you people should do earthquake research because the tsunami had just happened. And somebody else came and said, you should do vaccine research. Somebody else came and said, you should do tsunami research. Now, how much can we do with such a small faculty? And, it has 40 departments. And if you just divide 350 by 40, you're getting hardly 7, 8, 9, 10 on an average, some departments are larger. So this is a big issue that is not being addressed, which is the number of competent trained persons in India is actually very small. I mean, you compare this to probably a floor in MIT, which will have several hundreds of people of such caliber and more. So an opportunity that you have here at the doorstep, since you're a captain of industry, you're also seriously engaged with the question of academia, especially in Kriya University. It would be marvelous if you put together some program in Kriya, bringing together, distinguished academicians from Chennai, from neighboring areas. And also we need to train large numbers of people, not necessarily at these premier institutions, if I might use this word, but at the next level. We have so many brilliant people who are not having opportunities, and life in India is hard. So let us give them, we have to develop a sufficiently large number of highly competent persons. This would go through workshops, training schools, intensive education in a couple of these fields. I mean, in the final analysis, our real strength in this country is the brain power of our people, We have millions and millions of rather well-educated people at the level of 12th standard, BSc, etc., etc., after which it saturates and then there's a very sharp decline. So this problem, if it is addressed, I also happen to be on the scientific advisory board of a company in Bangalore, Avesta Gen, which is a biotech type company which also does research. One of the many things they do agriculture, they also do climate, crop research, as well as what's known as a Parsi genome project, because the Parsis are, as you know, an endogamous population who also have the gift of living to a very long age, and therefore to map their genome is particularly good for all of us. And of course, because they are endogamous, they also have a problem that they have concentration of certain diseases, and they also try to partner with Chris Gopalakrishnan Center for Brain Research, Alzheimer's, Parkinson's, all kinds of diseases which are hereditary and which get concentrated in endogamous populations. So I'm aware of these things, I'm aware of BIRAC, but it always comes back to the same thing. We are such a small number of trained persons. And if you could take note of this and do something about this, this would be really a great contribution.
Quickly.
We also share our last name, Anantanarayan Lakshman.
No, the first one is on that Lodha Institute that was mentioned. I think Ravindran was there. He's very familiar with that. What he has done is, Abhishek Lodha, who runs that huge real estate empire, he has given 20,000 crores to Lodha Foundation. 20,000 crores, which is 1/5 of his wealth. He is a very rich man. So, just 3 initiatives. One is he wants LMSI, Mathematical Sciences Research. Second one is Indian culture, the Vedantic culture, the traditional things, and then see if that can go into Ayurvedic medicine and things of that nature, early stages. And the third one is on sustainability. Sustainability, again research-oriented type of work, which I think he is collaborating with Soumya Swaminathan of MSSRF. So what is required is research proposals that can go to that institution. Okay, so there are people, V.K. Murthy is there. If there are proposals, ideas that you want, it's writing to him and seeking funding, seeking collaboration is something that would be, they're looking for it. They have the money, they don't know where to spend it, how to spend it. Just conducting seminars and calling all the people, that's not going to produce results. That's something that they realize. Fortunately, because the CEO of that company is a chief secretary from the government, he understands the social development aspects, and so he is likely to do that. The second point that I want to make is, just as it's true in corporates, big innovation does not come from big companies. There are few who have set up their own research centers like IBM, etc. In Indian companies, innovation always happens in small groups, in startups, in small companies. They are the people who are passionate. Big companies have their own problems to solve. They don't have time to worry about innovative this thing. That's the category that many of the IITs and some of the leading institutions are falling into. They're worried about raising funds, they're worried about graduating so many students, that numbers is there. As a result, innovation, it appears to be taking a back seat. But innovation and invention, more than innovation, which is application, invention, has to happen in institutions like IMSC and smaller institutions where a concentrated group of passionate people can work, and supported by funding from people like LMSI and other individual philanthropies. Once that develops, I think the research in this country will get to at least the next level and progress further.
Just one comment. Bhaskaran here, he cited Abraham Flexner. This is another issue. Many of the issues that face our society has not been addressed by philosophers or thinkers of our own society. We are having to quote somebody from 1920 from another country. It has nothing to do with us, and there is a big vacuum in terms of the thinking, you know. And I'm not just criticizing it. Along with some of my former students and also Daniel Wheeler, professor from Zurich, who's retired, we have been working on a manuscript where we are trying to address many of these issues of the nature of science, especially in India, as an example, because we are qualified to talk about it. Not that we are a particularly distinguished place or anything like that, although we account for 15% of mankind. So there are many issues that have to do with our society which are not commented upon by any one of us. Every one of us should take the responsibility, not merely quote Oppenheimer or quote this guy or that guy or Rothblatt or Flexner. We should all do it. We should address the problems of our people. And again, a place like Kriya would be an ideal place where you have a talented young set of faculty members to catch this bull by its horns. I have said a lot, so maybe Shankar, a much wiser and experienced person, has something to say.
No, I really don't have much to say on this issue, except that, when we discuss quantum computers and this, there's always a question, when is it going to happen? According to me, what is the hurry? Also, I'm a bit wary of revolutions, like, for example, the Industrial Revolution that took place end of 19th century. It improved the quality of life, like, with a huge impact on human. It had unknown environmental effects. Only now we know. When it was happening, there was no clue. So that way I also think that we are going through a communication revolution. There used to be telegrams we sent when I was a kid. That's a gone concept now. Letters are, the whole communication revolution we are really living through. But if you do it too fast, we may have maybe not environmental effects, but other social effects. Yeah, that's all. I think there's no need to be in such a big hurry. Let quantum computers take 200 years in coming. What's the problem?
We would like to see it. That's the problem.
So just curious about one comment that you made, about innovation being in small companies. Aren't IBM and Google a counterexample to this thing? They are like the biggest companies you can think of, but yet they are at the forefront of quantum computing. I wonder what you...
They're structured differently. They're structured very differently. That enables them to have that, a completely separate, IBM Research is a separate, completely different entity. They have no commercial pressures at all. Okay, they're not worried about the top line or the bottom line. The funding is liberal funding that goes from IBM to this thing, and this is, like you said, open-ended research. That is,
so they're like small companies.
Yeah, it's all like small groups that are working there. So that's a model. The other model for universities is, it could be Caltech. Caltech is another great example. It's not like a University of California, Berkeley, 15,000 people, 20,000 people, 4,000 people. That's all in Caltech, about 2,000 undergraduate program. They probably have the best undergraduate program, 2,000 researchers. And, NASA's Jet Propulsion Lab is there in Caltech. Amgen, the biotech company, came out of Caltech. So there are so many examples, and they have the credit for the largest number of Nobel laureates who have come out of Caltech, etc. So there, that sizes, that compactness is important. If you chase numbers, which is a problem we have here in India, that's a pressure. So the government has funded. Next IIT, what is the number? 2,000 students. When is it going to become 5,000 students? When is it going to become 10,000 students? There you cannot have quality in that type of this thing. So that's something that we have to measure. Maybe you need a set of institutions that produce numbers and volumes, a set of institutions that are very small, like the Caltechs, that do cutting edge research, that are well funded. Models have to be looked at.
Any other comments? Any comments? Any questions about any of the talks today?
Everything's clear.
I have a couple of questions which Shankar, I was just wondering about the anions and fractional statistics. Are there examples where this has already been applied in condensed matter systems, and it's like where we have these things realized?
Have they been found experimentally, you mean? So the quantum Hall systems, now statistics is very difficult to verify.
I see.
Because these are quasi-particles in the middle of a solid, you can't. But fractional charges have been found.
That's electromagnetic charge.
Pardon?
Electromagnetic
Electromagnetic charge, yeah. Of 1/3, 1/5, 2/5, and so on. So, and in the theory, they all go hand in hand.
I see.
So, fractional charges are a signal of fractional statistics.
I see.
Majorana fermions. There was a lot of news 6 months ago.
Yes.
Then, okay, please
Yeah,
tell me.
so that was one of my slides, that they have actually realized these
Majorana qubits.
non-abelian anions, I'm not sure whether it's Majorana fermion, in these quantum circuits. This Josephson junction type of qubit circuits. And they have, there they have verified braiding.
They are verified?
Braiding.
I see.
So these are not quasi-particles in a condensed matter system, this is an engineered system.
They are two-dimensional, right?
Yes, 2 dimensions, yes. Equivalent to 2 dimensions. I don't know physically whether that's circuit is, but
They are
mathematically.
minimal non-abelian anions, Ising Majorana. That's what they claim.
Oh, okay,
The Microsoft.
maybe, yeah. Google,
No, Microsoft, our friend, Indian chap. We'll check.
Chetan Nayak,
Chetan Nayak, yeah. Chetan Nayak.
that also was there sometime. So
Exactly.
this Google is a new one.
Oh, I see. Chetan Nayak, whom I know very well, he claims that they have seen Majorana fermion.
Yes, now I don't-
They have built a small
Yes.
chip and so on. And also another fascinating development is from China about boson sampling.
Bosons?
Boson sampling. They can evaluate permanents which are very difficult to evaluate very easily, but for some reason nobody has followed it up. It's a special purpose computer, but I keep telling people we should try it. I do not know if you have any comments about boson sampling. Okay.
Sorry, what is the significance?
You see, because even in high energy physics, how do you get statistics? By scattering experiments. Right, that's how, they are difficult to do in a condensed matter system because you can't do controlled scattering of quasi-particles.
And how is the Majorana nature, how is that?
So when in condensed matter person says Majorana nature, it has nothing to do with Lorentz invariance and the,
So the reality condition, that is still...
that's the only condition.
No, okay.
Yeah.
And
You look at the decay products, but that can't be done in condensed matter either. Because we can do a lot.
Yes,
of
yeah, that's right, yeah.
That's the problem. Why you.
Basically, you can't handle individual quasi-particles.
Correct.
I mean, you,
That's right.
This is about a complaint about our Indian institutions and so on. See, in math science, we kick people at the age of 60. People say they reach their prime at 75 or so, the peak. So I told Ajit Chaudhary in a meeting that quantum mission should spend some money and keep these quantum gurus for some more time, 10 years, 15 years. A small amount of money spent on them will be wonderful, because they are outstanding people. IIT, they keep them at 65, math science 60. But there are places in Princeton, people, as long as they live, they have an office. They can come and work. I think it should be possible, not for everybody, but those who want to do. So I'm making a request to people. So whenever you spend some money, think about employing these great people who are very still putting India in the world map. Thank you.
Any other thoughts, Shankar? So Anant, a question for you.
Yeah.
So you pointed out the fact that E plus E minus 2, pi plus minus the data is not agreeing with the G minus 2 and the lattice result.
Yeah.
Do you have any thoughts on what might be the reason why they're...
No, this is it's a puzzle which we have to resolve, or it may never get resolved. It's nobody knows. So over the next year or year and a half or two, I'm sure there'll be a couple of conferences where all these experts will be debating and looking at every single piece of the puzzle. So best not to say anything now.
Okay.
So, well, this is what makes the subject interesting. I mean, everything is solved and everything is settled. That's too boring. Well, you have to, I'm not going to say anything.
Not good to see.
Especially it's being recorded on YouTube.
Yep.
So regarding this boson sampling, there are a couple of issues there. One is that what will happen if there are noise in the preparation, in the measurement, in the processing, etc. So then, so the idea is that whether you get any quantum advantage by doing calculating the permanent, which is otherwise not possible so efficiently in the classical computer. Boson sampling is a bunch of photons are coming on interferometer, and then you are looking at particular outcomes. Okay. So the question is that what if there is some noise in this boson sampling problem, and it turns out that if there is some noise, a specific kind of noise, then boson sampling does not help you compared to the classical computation.
But it's a great achievement in the sense.
It is achievement.
Next step is.
Yeah. Next question is that how many photons you would require to achieve in boson sampling something which are not possible in the classical setup. And I have seen some works which says that at least 50 photons you need. 50 clean photons or something like that. Now this is very difficult, at this stage this is very difficult. I don't know about this Chinese experiment, what they are claiming. So in order to get something which has quantum advantage, quote unquote, you need something which is at least 50 or more than that. Yes, that is true. That is true. So boson sampling, if it can show some quantum advantage, it means that with lesser requirement than a practical quantum computer, you can do something which will give you, the quantum advantage. Yes.
Sorry, can you say what is meant by boson sampling?
So you have some, bunch of photons are coming on some interferometer, maybe beam splitter, phase shifter, etc. And then you have photodetectors there in the output. So you choose the output in such a way that it can give rise to the result of permanent calculation. So there is some notion which is like determinant in the permanent, which takes care of these photon states. Okay. So now apparently in classical computer this permanent calculation is difficult. Something like that. It's a hard problem.
And that
So this is a very specific problem.
Yes, yes.
just for calculating permanence.
Yes, it's a very, see, quantum computers are always problem specific. One cannot, at least to my knowledge, so far we don't have anything like universal quantum computer which can solve all the, nice problems. No. Yes, yes. So you will have to design a quantum computer to solve a particular problem.
No, but are there not universal gates?
Gates are universal. Question is not gate universality. Question is that, the design of the gates inside your computer should be such that which can address a particular problem.
Okay.
Unlike the classical computer. At least this is what my understanding goes.
So if you have the basic gates and you're able to interconnect gates, does that not mean that you can solve any problem?
To some extent, I agree with what he's saying. So you have, like in digital electronics, you have the two in digital electronics, there is only one universal gate, the NAND gate. For a quantum computer, you need two of them. One is a single qubit gate where you can rotate the state of the qubit on the block sphere wherever you want. And the second is the 2 qubit gate, which is that controlled NOT gate. Once you have these two, then you can build any quantum circuit for a given number of qubits. You can connect them with whatever limitations you have in terms of interconnection. You connect whatever and then optimize your quantum circuit. It's basically a series of gates that you apply on X, Y, Z qubits. Now, not all problems, you may be able to design a circuit which would be able to solve a particular problem, but it may be worse in terms of execution times compared to your classical computer. Now, by the definition of it, quantum computers are supposed to be for only specific problems which are very hard classically, whatever they call NP hard, this hard, that hard, those kind of problems can be solved there. Now, for example, if you want to find the structure of a molecule, if we do it on a classical computer, we go by first principles, some ab initio calculations, this, that, we use the understanding of quantum mechanics, and then we write long code, and then the thing just blows up in terms of the amount of time it takes depending on how many atoms you have in the molecule. But imagine a scenario where you do an analog simulation, meaning like a molecule, I design the connectivity between the qubits. Another molecule, I design the connectivity between the qubits. And then say I want to find the binding affinity of molecule A with molecule B, which is one of the big problems in drug design and all that. Now I design similar things on my quantum computer with an array of qubits, which looks exactly, which mimics that real life system. I bring them together and the system just evolves to its natural this thing and give you an answer of a resultant molecule. Or it may give you an answer to what is the probability of these two binding together or not, which is the drug design problem. You don't need the quantum gates you don't need to write a quantum circuit to do it. Quantum circuit, okay, I mean, it was motivated by the fact that we had the Shor's algorithm, which started the entire game of quantum computing. Basically, people started getting threatened by the fact that you will break the RSA algorithm. But the point is, you may not need RSA algorithm anymore. You have post-quantum cryptography schemes which can solve that problem anyway. So
do we have any example realization of this kind of a setup?
The molecule thing?
Yeah, where
I think these neutral atom quantum computing fellows are doing this. I think one of these Pascal or Qvera or one of them are trying to do this. Yeah.
successfully demonstrated?
No, just to, sorry.
I don't have the exact references, but yeah.
No, coming back to this universal quantum computer, in practice there will be difficulties, but in theory it is there, right? I mean, like a universal Turing machine. Yes, yeah. That's for a universal gate. No, I mean, independent of the realization, I mean, there's a theoretical concept of a universal quantum computer, right?
Yeah, yeah.
Maybe can I say something? So, when you say the universal gate set, it means that any unitary operator, because quantum evolution is unitary evolution, can be realized by a fixed set of elementary gate operation by their concatenation. Okay. So for quantum computation, any of the algorithm like Schwartz algorithm, Grover's algorithm, whatever you talk about, you need a specific type of unitary transformation, unitary gate operation. Okay. So which we call oracle or black box, whatever. So that unitary gate can of course be realized in terms of concatenation of this fixed set of elementary gate operation. But that doesn't mean that I build a computer with this elementary quantum gate operation, and with that gadget I can solve any problem like factorization or Grover search or something with the same computer. No, I can't.
So, yeah, that's what I mean.
Yes.
In practice, definitely not. But in principle, like, for example, this Turing machine,
Yes.
it's in the head.
Yes, it can. Yes.
But, I mean, even classically, there are universal gates, like he pointed out, that just with that one gate you can make any type of. But there's also a concept that putting those gates together, because when they talk about complexity theory, the theoretical computer scientists, they have a concept of solvability in polynomial time or not, which sort of, and similar concepts are there for quantum computers.
Yeah, it is there. Question is
Yeah, in this context, implementability is one thing, advantage is another thing. So it is implementable in theory. There is a quantum Turing machine. Whether there is advantage or not, it is problem dependent. Okay. Advantage over classical. Yeah. That is one thing. Secondly, he is pointing out is like the networking, how you network the qubits is usually dependent on what is your target problem. If you want to do quantum Fourier transform, you have to have certain topology of qubits. That is more efficient for that problem. It is a practical aspect. It's not a theoretical aspect. So it's a practical aspect. Yes. For example, if I want to entangle n qubits, star topology is the best because it can do simultaneous parallel CNOTs. But if you want to do something else, some other topology is better. So it is just a practical aspect.
There's no concept like in classical computers. You just want something that can implement C. Take an input from a programming language and give it an answer. Is there a quantum programming language?
Yeah, when we say that it is a universal quantum computer, theoretically it can implement anything. Yeah. It is possible. Yes, series of unitary transformation. Yes.
So people are working on this so-called compilers or transpilers for translating a real problem into a quantum circuit. Given the knowledge that you have n number of qubits and the connectivities that you have. Yeah.
You can just, one can do it in quantum computer also. That is not an issue. One can always do that. Okay, so, but the question is whether it is needed, whether it is efficient, all those questions are there.
I think he's put it nicely.
Yes.
It's implementable, but may or may not have advantage.
Right.
Sorry, I have to go to airport at 7. It was very nice meeting.
I am not deeply into that, so I can just broadly say some things about this. So The idea is like you are going to send single photons in either horizontal and vertical polarization or in superposition state, plus or minus, and you don't reveal that. Okay, so you are going to send either horizontal or vertical or plus or minus, okay, in that basis. And then the other party is going to measure in that individual's basis, and they don't initially reveal the basis to anyone. The basis is secret initially, and then idea is like once they make the measurement, so measurement the photon has collapsed in the recipient's basis. Once they make the measurement, after that they compare the basis publicly. So and then they and then they compare the statistics and all those things, and then you can prove that if there is interference in between, if there is invasive some spy is in between, then there will be disturbance, and then statistically you can find out that there is a invasion in between. So that's the quantum key distribution. That's the general idea. So it is like classically there is a issue that there is it is always possible to copy a classical message. Okay. However, there is a very powerful theorem in quantum information. It's no cloning theorem. So an unknown qubit cannot be cloned. Okay. So it's a very powerful theorem, and that comes into play here. So whoever is the middle party who wants to retrieve the information, that party has no way to copy that unknown information, and so any invasion is bound to disturb, and that is bound to disturb the statistics. And yeah. Yes, after not the results of the measurement, the basis, not the results of the measurement. They compare the basis, okay. Whether it is plus or minus, or whether it is plus H or V, horizontal or vertical. So that is sufficient. Yes. 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 Only bases are compared publicly, and basis has no information about the message. So that's the interesting part. And now, of course, many attacks have been developed. So there are different attacks. Anyway, some attacks are hardware dependent because you can spook the transmitter, you can spook the receiver and all those things, and anyway, and there are counter attacks and so on. There are security for those attacks and so on. The challenges are both in terms of the noise via channel, because these quantum networks which carry single photons, they cannot be transmitted. I think in the current technology it is like 70 kilometers or 100 kilometers. Beyond that you need to have a quantum repeater. Okay. Optical fiber, yes. And so apparently they have to have some amplification, and so again further transmit and so on. So there are such technological challenges, and so the other challenge is the bit rate. You can never beat the classical bit rate. So transfer of information, the rate at which you can transfer information is very small. It is, I think, 2 orders of magnitude smaller than the classical information. So, but then whenever you are passing the key, so that sometimes it is acceptable. And so that's why there are people want to start trying it, so that once you start trying, maybe gradually the field develops. They have also successfully demonstrated ground to satellite, and then satellite to ground. So that key distribution is also successfully implemented. There are several quantum satellites now. One is Chinese, and another is European satellite, and so there are many. I think ISRO is also planning one quantam satellite in the near future. Maybe it's next year or year after. So yeah, so there are many developments which are coming up. So the whole aim of quantum communication is to have the secure communication. So you have to distribute the key. So yes, message, see it is like this, once there is a key which is transmitted securely, then message can be encrypted in classically also. Yes. Yeah, you don't need to send the message also in that. Yeah.
This is radio communication, same way.
Yes, it is not radio, it is currently it is optical. So they are finding the band which is more efficient via atmosphere. Apparently first 2 kilometer is the challenging task, and I think they have chosen, I think Chinese one they have chosen something like 790 nanometers, something like that. So this, first few kilometers are challenging. After that, it becomes sparse and there are less water molecules, and so yeah.
The other thing is that one is this thing. The other thing is what happens if I send the key. If I already tell you the key, you go. So you carry the key with you, and then we start communicating. What would go wrong in that?
So the idea is like this: the message is theoretically the message is secure if the length of the message is same as the length of the key. Yeah. Anything beyond that, it starts becoming insecure. Yeah. At least. Yeah. I mean that's the theorem. Yeah, Shannon's theorem. Yeah. Because if you start using same key again and again, the key can be broken, and that's what happened in World War II, that Enigma was broken. Yeah. Yes, that's a theoretical concept. Yes, theoretical concept.
What we find in particle physics is that if you can have a system where meson oscillating to antiparticle and propagating, we found that there is no way until I have I used to call it noise, but that is this phase that nature has put to the weak phase. If I know the weak phase, I can solve everything, but I don't know it, so I can't solve it. So in principle, if I communicate in exactly the same analog, if I don't let that phase be known, only my party knows it, I know it. So my hardware has hardwired with it, but then next hardwire I change it. So I can, secure that. That's what we find. But this is analog, exact analog. I mean, this is a particle, antiparticle quantum system. It is evolving, and there I can somehow I find that is.
Maybe there is an analogy. Yes.
Yeah, there is some system that I find absolutely works.
Questions? No? Any final thoughts?
Thank you.
Yeah. So let's thank all the speakers of the day, the panelists, all the audience for the questions, comments. Thank you all. So dinner will be at 7:30? All right.